Assalamualaikum and good morning. Today we will continue with chapter 6. Plastic analysis was chapter 7. This influence line is chapter 6. Influence line is very important in the application for the design of structures that resist large live load and moving load. For example, bridge. This chapter discusses moving load from one point to another point. For example, load from vehicles moving on the bridge. An influence line represents the variation of the reaction, shear, moment, or deflection at a specific point in a member as concentrated force moves through the member. Okay. For this reason, influence lines play an important part in the design of bridges, industrial crane rails, conveyors, and other structures where loads move across their span. This is the link for the YouTube that shows what influence line is. You can go to this YouTube later. Okay. Influence lines for beams. There are 3 steps, basic steps to draw the influence line. But before we draw the influence line, again, this influence line is nothing like shear force diagram or bending moment diagram. Okay. So far, you have been dealing with drawing the shear force diagram and bending moment diagram due to static load. But this time around, you are going to draw the influence line for the moving load. How, for example, you are standing at one end of the bridge, and as you walk along the bridge, the load that you carry from your self-weight will cause the load variation along the span of the bridge. So this load variation is represented by the influence line. Okay, the procedure. First, we allow 1 unit load. We can put either 1 kilonewton, 1 newton, 1 kip, or 1 ton to move over the beam from left to right. And second, we find the value of the shear force or bending moment at the point under consideration as the unit load moves over the beam from left to right. Okay, so in order to draw the influence line, we have to assume there is a unit load moving from one point to the other point at the other end. Third, we plot the value of the shear force or bending moment over the length of the beam computed for the point under consideration. There will be a point to be considered, the point where we need to know what is the load acting at that point. Why we choose certain point? The certain point we choose based on the assumption or anticipation that that point will carry the most critical load. Okay. Variation of reaction RA and RB as function of load position. So this example 5.1 will teach you how to construct the influence line for vertical reaction at A and B. Okay, so now we have a beam 5 meters long, simply supported with pin support at A and roller support at B. Okay, so step 1, we assume 1 kilonewton moving from A to B. Okay, allow 1 unit load 1 kilonewton to move over the beam from left to right. Find the value of shear force at the point under the support reaction at A and B. And then plot the values in graph of influence line for vertical reaction at A, RA, and B, RB. Okay, so we already put 1 kilonewton there, assuming it moves from A to B. Okay, then we have to find the reaction RA and RB. Okay, so we don't have specific specific distance from A to the point here. So we take the distance as x because this x varied from A to B. Okay, so from the first static equilibrium equation, which is summation of force acting upward equal to summation of force acting downward, we have RA plus RB equal to 1. And then we have a moment at A equal to 0. So this moment at A is 1 kilonewton times x. That is clockwise. And we have another one, RB times 5, which gives us counterclockwise. That's why we have negative here. So 1x minus RB5 equal to 0. Therefore, RB is x over 5. Okay, so we have RB x over 5 with, okay, once we find the RB equal to x over 5, we know from this equation, equation number 1, RA is RA is 1 minus RB, which is x over 5. So the RA is 1 minus x over 5. Okay, so we can draw an influence line for both RB and RA. RB just now is x over 5. RB is x over 5, so we put it here. RB is x over 5. Then we will have to calculate the RB when x moves from 0 to 1 meter, 2 meter, 3 meter, 4 meter, until it reaches point B at 5 meters. So that's why we put the x here from 0 to 5. 0 is at A, 5 is at B. Since we know RB is x over 5, So when x is 0, RB is 0. When x is 1, RB is 1 over 5. 1 over 5 is 0.2. And so we repeat the same calculation and we find that at 5 meters, RB is equal to 1. Now we can draw the influence line. At 0, it is 0. At 1, it is at 5 meters, it is equal to 1. And we can put the coordinate from this table. Okay, so this is the influence line for RA. In a similar manner, we can find the influence line for RA by filling in the table X and RA. RA is 1 minus X over 5. So again, X is from 0 to 5. When X is 0, RA is 1 minus 0 over 5. So it is equal to 1. Okay, 1 here. And we repeat the equation. We get RA is decreasing from 1 at point A to 0 at point B. Okay, so this is the influence line for RA. It's easy, right? Okay, now let's go to example 5.2, variation of reactions VC and MC as function of fluid position. Okay, now we move one step ahead. This time we going to find the shear force VC and moment at C. Okay. Example 5.2, construct the influence line for RA, RB, VC, and MC. Okay, to construct the RA and RB, we have to find the RA and RB. Okay, that is RA and this is RB. Okay, don't forget we have to put one unit load, okay, at X. At X distance from A. Okay. Okay, now we take moment at A. Moment at A, first we have 1 kilonewton times X. One X and then minus 8 RB. RA is equal to MA is 1. Okay, let us let's see here. MB RA is 1 minus. So if I do MA, moment at A, equal to 1x minus 8RB equal to 0. Therefore, I will have RB is X over 8 RB. RB is x over 8. Okay, is it? Okay, so we have RB x over 8 here. From the RA plus RB equal to 1, we will have RA equal to 1 minus x over 8. Okay, so you will find that every time you have the beam problem like this, where you have to draw the influence line, the RA and RB is always in this term. Yeah? One of it will be x over the total length of the beam, and the other one will be 1 minus the reaction. Okay, so since we have RA and RB, we do the filling in the table just like example number 1 just now. But if you want to skip the steps, you want to draw a simple influence line, you just take x the minimum, which is 0, and x the maximum, which is 8. Then you substitute this x into the RA and RB equation, and you will get the value for that RA. Then from this table, we draw the influence line. This is the influence line for RA. For RA, the maximum is 1. The 0 is at B. Of course, it is like that, yeah? Reaction at A. So the maximum is at A. And it decreases. The effect of the reaction at A decrease until it has no effect at support B. Okay. Same with RB. The maximum RB for influence line is 1, which is at B. Then it decreases along the span of the beam until it becomes 0 at the other end of the beam, which is at A. Okay, so now how do we find the shear force diagram and also moment diagram at C? Okay, just now the question asks us to find the VC and MC at point C. So at this C, we divide the segment of the beam. We have the left and the right segment. Okay, and then to solve it, we only take the left segment, this one. Okay, so we have two conditions here. One is when 1 kilonewton is assumed to act on the left beam. So here you can see the 1 kilonewton acting on the left side of the beam. The second equation now, this is the second equation. We assume that 1 kilonewton acting on the right beam. That's why you don't see the 1 kilonewton here. Here you have 1 kilonewton, but in the second picture here, you don't have the 1 kilonewton. No 1 kilonewton. Okay, because for this second condition, we assume the 1 kilonewton is acting somewhere here. Okay, let me erase this. Okay, let's see the first condition where it is assumed that 1 unit load or 1 kilonewton is acting on the span from A to C. Okay, so first we have RA, which is equal to 1 minus x over 8, and then we have VC acting downward at C and MC acting counterclockwise at C. Okay, then we can find the VC from this equation here. RA upward is equal to total force downward, which is 1 kilonewton plus VC. Okay, we have 1 plus VC equal to RA. RA is 1 minus x over 8, so it is equal to 1 plus VC. From this we get VC equal to negative x over 8. Okay, then we we fill in the table. When x is 0, the VC is 0. When x is 2, VC is negative 2 over 8, which gives us negative 0.25. Okay, we leave that table for now. Okay, now we we calculate the moment at C equal to 0. Okay, moment at C, when we look at RA, we are going to have the clockwise moment. So RA times 2, yeah, the distance here is 2, the total distance is 2. Okay, 1 minus x over 8 times 2, and then that is 1 moment clockwise. Okay, we don't have any more clockwise looking from C, but we have counterclockwise. The first counterclockwise is the MC itself. The MC is counterclockwise, so we minus MC here in this equation. Another moment is from 1 kilonewton. You look from C, 1 kilonewton multiplied by the distance from C to that 1 kilonewton is 2 minus x, because here it is 2. Therefore, since here x, so this is 2 minus x. Okay, so now you have MC equal to 3x over 4. Again, we fill in the table where we'll get MC is equal to 0 when x equal to 0, and MC is equal to 1.5 when x is equal to 2. Okay, now we repeat the same steps in condition number 2, where we assume that the 1 unit no longer acting on this span. Okay, so again we start with finding the VC from summation of reaction upward equal to summation of reaction downward. We have RA is equal to VC, therefore VC is 1 minus x over 8. Okay, then we are going to find the MC. M at C is equal to 0, so we have RA times 2 clockwise, 1 minus x over 8 times 2 clockwise, And then counterclockwise, we have one moment only, which is MC. Minus MC equal to 0. Then we get MC is equal to -2 minus x over 4. We substitute the x equal to 2 in this equation. We get MC is equal to 1.5. And at x equal to 8, MC is equal to 0. Okay, now you can draw the shear force and bending moment diagram. Okay, influence, not the shear force and bending moment, yeah. You can draw the influence line for shear. This is not shear force diagram, I'm sorry. So the influence line for shear at C is, you draw, okay, you take this 0, from 0 to 2, and okay, from 0 to 2, and from 2 to 8. Okay, so from 0 to 2, we have VC 0.25. Okay, negative 0.25. That is why it is going downward from the x-axis. And then moment VC at, we look at the second table now. VC at 2 meters is 0.75 positive. That's why it goes up to 0.75, and it will then go down to 0. Okay, in a similar manner, we refer to table for moment from the first table here, and then from the second table here. Okay, let's see the value. At 2, 1.5, and 1.5. Okay. So from 0 to 2, the moment increased from 0 to 1.5, and then from 2 to 8, it decreased from 1.5 to 0. So this is the moment influence line for shear and moment at point C. Okay, so it is easy. I hope you will you will try this calculation. Okay, and until we meet again, stay healthy, stay safe. Okay, bye bye.